little explanation of our homework 3. Now you listen carefully here. One, I want you to prove the second matrix equations of motions are equivalent to the first matrix equation of motion. That means these two equations of motions, they are identical in the sense of from the input, say AG, to the output, say W and W dot, right? And also that the purpose of this design is to show you that the equation of motions are not unique. They are not unique. In other words, you can have all different forms to write your equation of motions, and they describe the same system. Okay, so that, because if you look at carefully the first set of equation of motions, like this set, this first set, you will see that your matrix, your mass matrix or your stiffness matrix, they are not symmetric. The second equation here, if we write in terms of matrix equations, then you can find out that they are symmetric. For example, the mass matrix in the second equation, if you write carefully here, the mass matrix for that, this becomes M plus MD, then MD, right? This is MD, and this is MD. That's the mass. That's the matrix. Mass matrix equation W double dot and WD double dot. And the damping matrix. If you look at carefully here, the damping matrix becomes zeta and zeta D, 0, 0, and W dot, WD dot, plus the K matrix, the stiffness matrix is K, 0, 0, KD, and that's W dot, equal to something else. This is just then equal to M plus MD. Then this is this minus MD. That's AG. Okay. So if you look at that second equation there, you have mass matrix, that's a symmetrics. You have your damping matrix, zeta, zeta D, and that's a symmetrics. And you have a stiffness matrix. And this is different from what you have seen in my note, right? But the first equation, if you look at the first equation here, and if you look at these equations, you will find out that they are not symmetric matrix. Well, you can try it out. Yeah. Right? You can write it out and see what happens. But again, they are equivalent. Normally, we like to write the system equation of motion in symmetric matrix form, like this. That's what we normally do. Now, the first set of equation, you can see that you can derive it from Newton's laws very easily. That's how it shows here. Okay. And this homework just show you that if you have AG, that's like earthquake. The AG is accelerations. If you have AG, you have the accelerations that tells you to from the ground, and that's the equation motions. And of course, that the like 101 building, it won't be like a M zeta K. That's it. The single values. That won't be like that. However, maybe there's a significant mode, we call mode, that we can represent it in terms of just M, zeta, and K. We say now 101, we concern only one frequency. And that's what I designed just one frequency a system for you. So to simplify your homework, that's the purpose. And this is a simple problem. If you know how to solve first one and second one, this one is very easy to do. Have any question about this homework 3? Yes.
So WD is the absolutely motion or the relative?
That's good questions. If you write this way, this is relative. It's not absolute. So, alright, that's good questions. WD is a relative displacement from is relative to what? Relative to the top of the beam. That means the WD is the displacement you look at from the tip, from this point. And W is the absolute displacement. You look at the W is absolute displacement from the ground. And WD is not the displacement look at from the ground. You look at from the tip, from this point, the top of the beam. Okay? So that's where you write it. I think this is good questions. Yes. If you look at from the ground, if WD is the absolute displacement, then your matrix will be the coupling will be in the K matrix. It won't be in mass matrix. So that's one way to do it. We'll talk about this later in other chapters, more detail. Understand now? Yeah. So the reason why I choose WD is relative. It's easier to write the Newton law because KD, WD, W has to be relative. Otherwise, you cannot write the minus KD, WD for the spring force. Right? You understand now? Any other questions? Okay, so we're in peace? Right, okay, we're in peace now, right? Okay, let's look at this. We end up, last week, we end up here. Today we have a lot of things to talk. I think last week we end up here, and then we did talk about this, right? Let me try to do this back there, so you don't see it. Right. So last week we talked about this chart. We define the poles and zeros in this chart. That's for also this. I show this is for second over 2 degree of freedoms. I need to explain a little bit later, but this is we in a mechanical system is we talk about 2 degree freedoms, and we have 2 balls. If we have 2 degree freedom, we have 2 balls like this. We have 2 degree freedoms. We're supposed to have 2 balls, and that's this is also a 2 degree freedoms. One is from the system and one from the TMB. All right, let us continue. All right, multiple degree freedoms. Assume we have more than 2, 3, 4, 5, the 101, the building 101. You know, building 101, how many degree freedom do you have? How many? Building 101. How many degree freedom do you think? Do you think the 101 has? You want to make any guess? 1, 2, 3, 5, 6, 7, 8, 9. How many?